Hi, ladies and gentlemen. Welcome to our next lesson here. We're going to start into section 6.4 in Professor Strang's textbook, which is covering symmetric matrices. And as he points out in the text, symmetric matrices have a lot of applications in science and engineering, and they have tremendous amount of structure associated with them, which is really what we're going to explore today. And next lesson, we'll talk about positive definite matrices, which means that we're going to have the combination of both symmetric and positive definite, as well as semi-positive definite. But that's for the future. So to start, let's take a look at what we have here for the beginning of section 6.4 with symmetric matrices. I'll leave you to read the details, and I will tell you the pieces. Remember, you want to pause the video right now if you have not yet skimmed through section 6.4. It's only about 7 or 8 pages, and just to get your idea of what it is we're going to be talking about, you want to take some time and 5 minutes and just look through the topics that we're going to discuss today. The nice thing, as we discussed previously, Professor Strang provides kind of an overview of where he's going in the section. And so there's material up front here that discusses the symmetric matrices and kind of the big things that he wants you to pull out of the text. One thing I wanted to look at is item number 5, which has to do with uh, symmetric matrices when we're talking about complex matrices. So he uses S to designate symmetric matrices. I will let you know that this might be a little bit confusing in the future because we will also use S on occasion for the singular values. Although in the Strang text, he uses the Greek letter sigma, the capital sigma. And so we will do the same thing, but you'll see in the MATLAB documentation, they oftentimes use the S matrix for singular values. So a matrix that is symmetric just satisfies this definition. It's equal to its transpose in the case where S has complex values. So of course, in what we've been talking about in 344, we've restricted ourselves to the entries of S being real numbers, and we will continue to do that. I just want to explain the note in the number 5 here in the beginning of section 6.4, where he notes that in order for a matrix to be symmetric, if it contains complex values, this has to be true. So the matrix has to be equal to the transpose with complex conjugates. And complex conjugates are important enough for us to make sure that you understand what this means. So let me just tell you initially, a matrix that satisfies this condition is actually written as S equals SH, where H is the complex conjugate transpose, and it is called Hermitian. So Hermitian is exactly the same as transpose when the matrix is filled with nothing but real numbers. So it's only in the case where we have a matrix that contains complex entries, complex numbers for its entries, that we even worry about the Hermitian. Um, that is not what we're going to talk about in this class, but I want you to be aware of that because you will see a lot of this notation, or the even more popular notation is the asterisk. So you'll see this notation, which means Hermitian. So again, it's complex conjugate transpose. So let's take a look at what it means for complex conjugates. So complex conjugates are quite simple, and we've already talked about this with respect to eigenvalues and eigenvectors, because our eigenvalues and eigenvectors come in complex conjugate pairs. So a complex conjugate for an eigenvalue a plus ib is written with the bar over the top. That's complex conjugate, not to be confused with the vector symbol. Right? So I will try to make it very clear that this is different from the vector symbol. The complex conjugate, and of course in the case of lambda, it's just a number, so it's not a vector anyway. The complex conjugate is simply a minus ib. That's all. So let's talk just a little bit about this because most of you have not seen this type of information. The way we generally graph complex numbers is we have a real axis, which contains the real numbers, and we have an imaginary axis, which contains the imaginary numbers. So something like a plus ib would be here, where it's over a distance a on the real axis and is up a distance b, a positive b, in the imaginary axis. So the complex conjugate of this number, graphically speaking, is right down here. It's a minus ib. That's the complex conjugate. It is the same number that is reflected across the real axis. And the reason that this comes up so frequently in complex numbers are the following two items. First of all, anytime I add two numbers together along with its complex conjugate, right? So I have a number and its complex conjugate that I'm adding together. In this case, what you'll see is I have a plus ib, and I'm adding to that a minus ib. And the result of this, of course, is a real number. So anytime I add a complex number with its complex conjugate, I end up with a real number. The same is true when I multiply. So if I take, let me not give it the sub 1 designation, I multiply in a complex number times its complex conjugate. It doesn't have to be eigenvalues. I'm just using the lambda symbol because that's what I was talking about previously. But it obviously applies to any complex numbers. When I do this, I have a plus ib and a minus ib. This is equal to a squared, and then I have a plus iab and a minus iab, and then a minus I squared b squared. So the terms here cancel, and what I'm left with is a squared minus I squared b squared, which is a squared. I squared is negative 1. So the negative of a negative 1 is a plus 1. Again, I have a real number. So the sum of a number with a complex number with its complex conjugate is a real number. And the product of a complex conjugate with a number and its complex conjugate is also a real number. Complex conjugates play an important part of complex analysis. Now that's not this class, but it does come up because of the fact that our eigenvalues and our eigenvectors always come in complex conjugate pairs. So anytime I have lambda as an eigenvalue, as we discussed previously, I'm guaranteed to have its complex conjugate as an eigenvalue. All right, so that's discussing, and we'll discuss a little bit more about this because this idea is integral to some of the realizations that we have with respect to symmetric matrices. But for right now, let's just continue with the text. So in the blue box are really, he just gives us the big results right up front. And the big results are the fact that we have, in a symmetric matrix, we always have real eigenvalues. We never have complex eigenvalues. The other thing we have is we always have not only a linearly independent set of eigenvectors, but an orthogonal set of eigenvectors. Remember, we can scale the eigenvectors to be any length we want because any scalar multiple of an eigenvector is an eigenvector. So we generally scale them to be unit vectors. We can't, however, change the directions. But in the case of a symmetric matrix, the directions are ideal. They are orthogonal to one another. So the set is mutually orthogonal. Every vector inside of the set of eigenvectors is orthogonal to the other eigenvectors. All right, let's take a look at what else we have. So moving over to the next page, we have this conversation about the spectral theorem, and Professor Strang brings up the spectral theorem as it relates to symmetric matrices, which is fine. But I will let you know that spectral theorem actually applies to all matrices. So we have this term called the spectrum of a matrix, and more generally, we have spectrum of a linear operator. So any linear operator has a spectrum. And the spectrum tells us a lot about what the operator does as well as its stability. All ideas that are beyond what we're talking about in this course, but I want to make sure you're comfortable with the terminology. So in general, the spectrum is quite easy. It's just the set of eigenvalues. And so it's related to the eigenvalue decomposition. And the eigenvalue decomposition, which we call the eigensystem is really made up of two things, right? It's the eigenvalues and the eigenvectors. And as we discussed previously, the eigenvectors give us a basis in which we can take the action of the matrix and we can diagonalize it. So we can uncouple the different attributes of the linear transform as long as we think about it in the right basis. And that basis is the set of eigenvectors. Well, the spectrum, because it's the eigenvalues, gives us that amount of compression or expansion along the new basis vectors that we have found in the eigenvectors. And that's just called the spectrum of a matrix. So he talks about that, and then he makes this comment in here, right about here, which says, look, we have to prove this, right? This is so important that we have to prove it. Well, we're in Math 344, we don't have to prove anything. And in fact, we're not going to prove this, but I do want to take a moment to highlight some of the items within the proof that illuminate what's going on. So it's the same as all the other proofs we've done in this class, which is to say you don't need to be able to reproduce them, but I'm going to show you the information that provides some additional insight and some additional intuition into what we're talking about. So back on page 339, make sure you take a look at the example that he has there, because he demonstrates quite clearly what we were talking about with respect to symmetric matrices. So just two ideas associated with symmetric matrices that I want to make sure that we have a good handle on. One of them is the fact that all of the eigenvalues are real. So every eigenvalue is real. And then the other one is the fact that all of the eigenvectors, which I will call Q, because they're going to make up what we call the Q matrix, which is kind of a generic linear algebra use of a matrix letter to represent an orthogonal matrix. But anytime that we have two eigenvectors that are not equal to one another, they are perpendicular. So these two ideas both stem quite easily from the fact that we have a symmetric matrix. So let me start with the following. Let's say that I have some eigenvalue and eigenvector for my symmetric matrix S. So what I know because of this, and what I'm focusing on here now, is the argument for the fact that we have real eigenvalues all the time. So from this, I know that I also have the complex conjugate, and I'm going to take the complex conjugate of both sides. Of course, the complex conjugate of S is just equal to S because we are limiting ourselves to S having only real numbers. And then this vector, we're talking about the complex conjugate. So taking the complex conjugate of an equation is something that we can do. And what we see here is we have one eigenvalue and we have its complex conjugate eigenvalue. And of course, the eigenvector that's associated with the complex conjugate eigenvalue is the complex conjugate eigenvector. And we already knew this, we talked about it previously. What I want to do over here is I want to take the transpose of both sides. So when we do that, we end up with this, and I apologize for the notation, but it's still the Q vector. It's the complex conjugate transpose. And now you see why we give it a new name, is because this comes up actually quite frequently. This is the Hermitian. And then S transpose is equal to, and then I have lambda, and that's the complex conjugate, and then the Q vector, again, complex conjugate transpose. And what we can see is, because S is symmetric, and this is really the argument that makes all of these things work out, because S is symmetric, this is, in fact, looking like this, where, again, we have complex conjugates on everything, but S is equal to S transpose, so I've just made that swap here. And now what I'm going to do is right multiply by Q. So if I right multiply this by Q, the vector transpose S and then the Q vector, is equal to the complex conjugate of lambda, complex conjugate of Q transpose multiplied by Q. And at this point, I'm done taking a look at this. We'll continue with that in a minute. What I want to do is come back to my original definition here for the eigenvalue and eigenvector, the lambda and the Q. What I'm going to do here is left multiply by the complex conjugate transpose. So I'm going to left multiply both sides of this equation by the complex conjugate transpose. And now you can see where we're headed with this. Lambda, of course, is not affected. This is the complex conjugate transpose times Q. And it's easy to see that we have the same quantity here, which means that these two things must be equal to each other. So we have lambda, and then we have the Q vector complex conjugate transpose times Q is equal to the complex conjugate of lambda, and then the Q vector complex conjugate transpose times Q. Thinking about what the complex conjugate transpose times Q is, that is just a number, right? So the transpose of a column vector is a row vector. So I have a row vector multiplied times a column vector. That is a dot product, and that's going to give me a number. So I have lambda multiplied by some number is equal to, and it doesn't matter what this number is equal to lambda complex conjugate times the number. Well, the only way that this is possible, I can divide out the case, the only way that a number is equal to its complex conjugate is if it's a real number, is if the complex part of it, the imaginary part of it's equal to 0. So what I know then is lambda is real. And this is the proof that Professor Strang provides. I just wanted to give you all of the detail in the content here. So it's fairly straightforward. I'm not sure he provides all the details. That's what I wanted to backfill for you. Now let's take a look at the fact that we have eigenvectors which are orthogonal to one another. So now what we're going to take a look at is the fact that we have two eigenvectors which are not the same. So we have distinct eigenvectors associated with distinct eigenvalues. And we're going to proceed in the same manner as we did previously. What I want to do is take the transpose over here of both sides of the equation. So this is going to give me a Q2 transpose, S transpose is equal to lambda 2 and a Q2 transpose. Now what I want to do is multiply on the right by Q1. So we have a Q2 transpose. Remember, now I have S, because S equals S transpose. This is again the symmetry coming into play. And I'm going to right multiply by Q1. So this gives me a lambda 2 and then a Q2 transpose Q1. But by the definition of eigenvalues, I know that this is lambda 1 times Q1. So substituting in here and then pulling the lambda 1 over, we have lambda 1 and a Q2 vector transpose Q1 vector is equal to a lambda 2 Q2 vector transpose Q1 vector. Again, this is a number. And what we see, let me just do a subtraction. I'm going to subtract this side from both so that I have 0 is equal to, and now I have lambda 2 minus lambda 1, and this is multiplied times Q2 transpose Q1. So I've just subtracted this off of both sides here. And in the case where I have 0, then either this thing is 0 because I have a product here, or this number here is 0. There's no other alternative. In order for this equation to be 0, I either have a 0 because the eigenvalues are equal, or I have a 0 over here. And because we assumed initially the eigenvalues are not equal because the eigenvectors are not equal, that leaves us with only one possibility, which is the fact that as long as the eigenvalues are not the same, so the eigenvectors are not the same, we have the dot product between the two eigenvectors is equal to 0. And that proves that the eigenvectors are orthogonal to one another. So these are the ideas associated with what we're doing with respect to symmetric matrices. These are really the two big properties. Always real eigenvalues, always orthogonal eigenvectors. The result of the previous items then is actually quite significant. What we end up with is we have the eigenvalue matrix, the eigenvector matrix Q. So this is the matrix whose columns are the eigenvectors, is equal to Q times lambda. And if I apply Q inverse, S is equal to Q lambda Q inverse. But it turns out that if the columns of A are all perpendicular, okay, so all columns are perpendicular to one another, right? So all columns are mutually perpendicular. So as long as they're not the same column, then they're perpendicular to one another. That means the matrix is called orthogonal. And an orthogonal matrix is a matrix where the inverse is actually equal to the transpose. So these types of matrices show up all the time in applications and are extremely fortunate for us because of this property. We can calculate inverses for free. We talked earlier in the course about the difficulty of calculating inverses and how we really don't use inverses very often because of the extreme difficulty and expense in calculating them. In the case, however, when we have an orthogonal matrix, then we end up with something that is really easy to calculate. So what we can do for a symmetric matrix is decompose it into something that looks like this. Moreover, an orthogonal matrix is associated with a rotation. So we talked previously about change of basis, and this is the same thing. If we diagonalize a symmetric matrix, we are still doing change of basis. But this time the change of basis, because, and this makes sense if you think about it, because all of the columns are orthogonal to one another, and we're starting with the standard basis where all the columns are also orthogonal to one another, then this Q matrix is just a rotation. Whether it's in 2 dimensions or 3 dimensions or 300 dimensions, it's a rotation. And so our change of basis is a simple rotation. Then we are going to scale each one of the new basis vectors using lambda, and then we're going to rotate. That's what the the diagonalization of this matrix is going to give us. So there's a little bit more here in Strang where he talks about that. And let's move on to this next result here, which is still true regardless necessarily of the eigenvalues and eigenvectors, but in this case, it's quite easy to see that because of this structure for a symmetric matrix, what this means is every symmetric matrix can be written as the sum of a bunch of rank 1 matrices. We already knew that. But these rank 1 matrices have a special property associated with them. So here we're going to take the sum, I equals 1 to n, of the eigenvalues multiplied times these, I have the transpose on the wrong side, multiplied times these outer products of the same eigenvalue. So the eigenvalue and its transpose. And this is an easy way for us to be able to calculate. So if you go back and think about, in general, A was equal to x lambda x inverse, well, the columns of, or rather the rows of x inverse are not related to x in any way that we can necessarily discern. So we can still construct A as a linear combination of the eigenvectors, right? Each eigenvector multiplied by the appropriate eigenvalue multiplied by the row of x inverse. That's a bunch of rank 1 matrices. We can still do the same thing. The problem is we don't know what that is. There's no easy way for us to find it. Because the orthogonal matrix Q is its inverse is equal to its transpose, we know exactly what those rows are. Those rows for Q inverse, which is Q transpose, are just the columns. So what I really have is this is the eigenvector as a column, this is the eigenvector as a row, and I have a series of rank matrices that I can connect together in order to come up with my symmetric matrix. And we'll talk about that a little bit more. I want to finish up here with the rest of section 6.4. So we have the conversation in the middle of this page, right? So he's talking in here about the fact that we have complex conjugate pairs for our eigenvalues and eigenvectors. But we already know that. So since we already know that, you can look through the example. He does a nice example with a rotation matrix, but it's information that we already understand. All right, let me just walk you through an example here where we take a look at a symmetric matrix and look at this diagonalization idea that we have right here and the fact that we're computing these rank 1 matrices. So let me do this. A is equal to random integers, and I'm going to use -5 to 5 for those values. And I'm going to make it 4 by 4, so something that's a little bit bigger than what we've been doing. I can create a symmetric matrix as A transpose times A. So A transpose times A is always symmetric, regardless of what matrix A I start with, right? So I have this symmetric matrix, which we can see here. Now what we're going to do is find the eigenvalues and eigenvectors for this. So using the eig command, we're going to end up with the eigenvalues and eigenvectors. And we can see here, the eigenvalues are given. Generally, MATLAB gives us the eigenvalues kind of in increasing order. And we can see the associated eigenvectors, which happen to be orthogonal, right? If we don't understand that or don't believe it, we could take the dot product, for example, of the first column and the third column of V. And what we better end up with is 0, because we're guaranteed that these things are orthogonal to one another. MATLAB already gives us in V, which we are calling Q, so let me set Q equal to V so we have a consistent set of ideas here. And this is our eigenvector matrix. So what the summation tells us, what this item right here tells us is we can approximate S as the set of eigenvectors multiplied as outer products with themselves multiplied times the eigenvalue. So let's start with the first eigenvalue and see how this works out. We'll remind ourselves what S is. And what I'm going to do then is take the fourth eigenvalue, which was the largest, and multiply this times the fourth eigenvector, which is the fourth column of Q, and that same column but transpose so that I have an outer product. So now I have the eigenvector, I have an outer product that I'm building here, and I'm going to multiply. So this is the first approximation to the x vector. And we can see that it's okay. It's not really great. But one thing that's interesting is it's guaranteed to be symmetric. Because of the fact that we're using the eigenvector as both the column vector and as the row vector, we are guaranteed to have something that is symmetric. So the next eigenvalue was of the size 36. So we're going to do the same thing. Let me copy what I have previously here. And we're going to take our answer and we're going to add to it the third eigenvalue multiplied times this outer product with the third eigenvector. So when we do that, we end up with something that is a little bit closer to what we're looking for here with our symmetric matrix. So one more time, and this time I will use the second eigenvalue. So now I will have added 3 of the 4 eigenvalues in, and we end up with something that looks like this. So looking at S, we can see this is pretty close. We have a 41 versus 42. We have a kind of a 12 instead of 13. We have a 35.5 instead of a 34. So we're pretty close. Now let's finish it off with the last eigenvalue multiplied times the outer product of the associated eigenvector and its transpose. And we can see we end up with this matrix here. Let's take a look at S. We have the same matrix. So we're getting, every approximation, we're getting closer. and all of the approximations are symmetric matrices. So this is kind of the idea that we're going to go with when we start looking at some of the information associated with singular value decomposition. So now what I want to do is take a look at the last 2 pages that are in the section here. And what I'm going to talk about, I really don't want to spend a lot of time on the pivots, but I do want to show you an example and really kind of emphasize this item down here where he's talking about S is equal to a lower triangular matrix times a diagonal matrix times the transpose of a lower diagonal matrix. So let's take a look at a specific example. So here's my example. And what I want to do is I want to do Gaussian elimination on this. I want to come up with the LU decomposition. So for the LU decomposition, you remember I'm not going to swap rows, and I'm also not going to try to change the pivot into a 1. All I'm going to do is multiply by the matrix that will end up preserving that top row, which is going to be 1, 0. That's going to be my top row, and that's going to give me a 6, 2 over here. And then I want to make a pivot down here. I want this to be a 0. So in order to do that, I'm going to need to multiply that top element by negative 1/3. Negative 1/3 times 6 is going to give me a negative 2. Added to 2 is going to give me a 0. So this is my Rockanar matrix that we discussed before. And this is some symmetric matrix S. And what I'm going to end up with then is I have a negative 1/3 times 2 is a negative 2/3 plus 3. 3 is 9/3 minus 2/3 is 7/3. And then you remember the reason that we do this for the LU decomposition is the fact that I can now write my matrix as, symmetric, of course. I can write my matrix as L is exactly the same matrix except I change the sign on all of my off-diagonal terms here. So this is just a 1/3 and then that's a 1 and a 0. And then I'm left with a 6 and a 2 and a 0 and a 7/3. All right, so what we have for the decomposition where he's talking about S is equal to L diagonal L transpose is actually related to the LU decomposition. So we have S is equal to LU, and we're going to build U as the diagonal matrix times the lower triangular matrix transpose. So that seems a little ridiculous. Let's try it. Here's L, here's U. So we're going to take L, 1, 1/3, 0, 1. We're going to take only the diagonal elements from U. We're going to take only the pivots. So the pivots are 6 and 7/3. Those are the pivot values. And then, of course, we're going to take L transpose, which is 1 and a 1/3 and a 0, 1. Okay. And what we have is, at least what he tells us, is that this is going to be equal to S. That this thing is going to be equal to our symmetric matrix. So this is interesting, right? This is LDL. We can see the determinant, right? Just as we did previously, the determinant of S is equal to the determinant of this product, which is the product of the determinants. And the determinant of L is 1, and the determinant of U is the product of the pivots. So that's one item that he emphasizes right up at the top of section 342. And besides the LDL transpose decomposition of the matrix is probably the most important thing on this page, where he reminds us that the determinant is the product of the pivots, which is also equal to the product of the eigenvalues. So let's take a look at whether or not this actually works out. We end up with a 1, a 1/3, a 0, and a 1, and then we'll take this product. So taking the first column is going to give us a 6, 0, and then a 1/3, and one copy of the second column. So a 1/3 copy of the first column and one copy of the second column gives me a 2 and a 7/3. And we can see immediately we're back to our LU decomposition. So the reality is the U is this diagonal elements, which are the pivots, multiplied times the transpose of the lower triangular matrix that we already found. So this is another matrix decomposition. So we have lots of matrix decompositions. The reason I wanted to emphasize this one is because it ties together some of the things that we did earlier in the course to this information associated with eigenvalues and eigenvectors of the symmetric matrices. I'll leave you to read the rest of the material that is here, and let's take a look at this last page. So the last page covers, and again, of course, he provides us the review of the key ideas, which is quite nice. But this covers the fact that what we had for diagonalizable matrices previously is if we have repeated eigenvalues, those eigenvalues have linearly independent eigenvectors. As long as we have a full set of linearly independent eigenvectors, we can diagonalize any matrix. And of course, we're talking about a square matrix because eigenvalues and eigenvectors only apply to square matrices. What this tells us is if we have a symmetric matrix, which is by definition square, if we have a symmetric matrix, it is always diagonalizable. Even when we have repeated eigenvalues, we can still diagonalize the matrix. That's the information that's provided here. Other than that, the last thing down here is actually quite important when it comes to doing linear algebra, but it is something that we are not going to spend any time on. It's called the Schur decomposition, yet another decomposition. And the Schur decomposition is an effective method for locating eigenvalues when we have matrices what the eigenvalues are. All that I'll say is the Schur decomposition for a matrix is we can always take a matrix, and this is true whether it's symmetric or not, and we can reduce it to some orthogonal matrix multiplied times a triangular matrix, which he represents as T, and then Q, and this is the Hermitian, because Q could have complex numbers in it. If we have complex eigenvalues, we could have complex eigenvectors, and so this is true, but we need the Hermitian. And remember, the Hermitian, one more time, is the complex conjugates transpose. So not really part of the course, but I just want to let you know that that is an important decomposition that you might see if you study more linear algebra when you get to graduate school. All right, so that's really what we have for this material. There's some additional information you want to make sure and read through it. There are some things in here. He talks a little bit about projection matrices. Anytime we talk about projection matrices or you read about projection matrices, you can just skip that material because we haven't discussed projection matrices in this class. So anything that looks like it's disconnected from what we've done previously, you don't need to worry about that. And the homework problems are a good guide to keep you focused on the things that I really want you to pay attention to inside of these sections within the Streng text. All right, let's take a look at the questions for today. We have these questions associated with eigenvalues and eigenvectors of symmetric matrices. And then also kind of how we can tell matrices are symmetric to begin with. So take a look at these questions, and if you want to hold on, I'm going to work another example just to take a look at how we find the eigenvalues and eigenvectors for a symmetric matrix or two. All right, thanks for those who held on. We're going to take a look at this symmetric matrix again, and we're going to solve for its eigenvalues and its eigenvectors. This is 6223. I recommend that you practice a few of these by hand because it's going to help you build your intuition with respect to what's happening with the eigenvalues and eigenvectors. So remember, we're going to take the determinant, in this case of s minus lambda I, and we're going to set it equal to 0. That's how we're going to find the eigenvalues. So we have a 6 minus lambda and a 2, 2, 3 minus lambda. And what you'll notice in this situation is we're going to take the determinant of this, set it equal to 0. This is 6 minus lambda and 3 minus lambda and then a minus 4. And as we go here, then we have lambda squared. We have minus 3 minus 6 is minus 9 lambda. And then we have 4 and we have, what, 18? 18 minus 4 is a positive 14 set equal to 0. And this factors quite nicely into a lambda minus 7 and a lambda minus 2. Continuing on then, we can see that lambda is equal to 7 and 2. When lambda is equal to 7, let's find that associated eigenvector. So remember, we're going to do s minus lambda I times the eigenvector is going to be equal to 0. And I will stick with the q's in this case because I know the eigenvectors are going to be perpendicular to each other, and I'm going to end up building what I call the Q matrix. So in this case, we're going to subtract 7 off of the diagonal, and we're going to end up with 6 minus 7 is a negative 1, and a 2, and a 2, and then a 3 minus 7 is a negative 4, and that's multiplied times q1 is equal to 0. And so, and that's of course the 0 vector. So in this case, q1 vector is going to be quite simply 2, 1. That would be sufficient, and I can check it against the second equation. 4 minus 4 is going to be equal to 0, and I'll be set for my first eigenvector. So from here, I already know what my second eigenvector is going to be, but let's verify. I know it has to be perpendicular to this one, but let's check that. So lambda 2 is equal to 2, and I'm going to subtract that off the main diagonal. So we have a 6 minus 2 is 4, so that's a 4, 2, and then a 2, and 3 minus 2 is 1, times q2 will be equal to 0, and in this case, q2 is going to have to be equal to a 1, negative 2. And we can verify against the second equation that that certainly is going to work. And then we see that q1 and q2 are orthogonal to each other, as we have to have. So what this gives us then is the decomposition, the fact that 6, 2, 2, 3 is equal to, and I'm going to build the Q matrix here. So this is a 2, 1, 1, negative 2, and I'm going to scale each of those vectors by a square root of 5. So I have a 1 over the square root of 5 that I've included here. And then we have a 7, 0, 0, 2. And then I'm going to multiply by Q transpose. And Q transpose is going to be a 2, 1, 1, negative 2. And again, 1 over the square root of 5. So looking at these things, we can take a look at them and we can see that we would have these two things give us, if we multiply Q times Q transpose, the identity matrix. So this is what it comes down to. S is equal to Q, and then sigma and Q transpose. Let's work up one more example. So I've written out our next matrix here, which is the 2, 3, 3, 10 matrix. And again, it's symmetric. Using the definition for how we're going to find the eigenvalues right here, we're taking a look at this determinant of this matrix, which is S minus lambda I. We're going to set that equal to 0. Writing out the determinant, we have this, and then I've simplified, which again, this factors conveniently. So this is going to be what? Lambda minus 11 and lambda minus 1. So in this case, we end up with 11 and 1 as the eigenvalues. So if we go back and take a look at our original equation, then let lambda 1 be equal to 11, we're going to use the S minus lambda times I multiplied times the eigenvector is going to be 0. So when I subtract 11 off of the main diagonal, I have a minus 9 and a 3 and a 3 and a 10 minus 11 is going to be a negative 1. And we can see very clearly that we're going to end up with an eigenvector here. In this case, Q1 is going to be equal to 1, 3. Again, we automatically know what the second eigenvector is going to be, but let's verify. Lambda 2, it's going to be orthogonal to this, right? We know it's going to be negative 3, 1. We know it's going to be negative 3, 1 before we even start. But let's verify. So lambda 2 is equal to 1. A minus lambda I, we're going to have a 1 and a 3 and a 3 and a 9 times Q2 is equal to 0. And then as we knew, Q2 is equal to a negative 3, 1. So again, we see that the eigenvectors are orthogonal to one another. And this gives us the Q matrix, which we can construct. If we want to turn these into unit vectors, we just divide, and this is how I do it. I kind of do a post multiply here by the scalar of the length. So 3 squared is 9, 9 plus 1 is 10, so the length of this vector is square root of 10. So I multiply by 1 over the square root of 10, and I automatically have a unit vector. Same thing here, right? Length is 10, so I multiply by the square root of 10, or rather divide by the square root of 10, and I make it a unit vector. So ultimately, I end up with 1, 3, negative 3, 1. That's equal to Q, and it's all those numbers are multiplied by 1 over the square root of 10. So that's my matrix, which is an orthogonal matrix. And I've made it into a set of unit vectors as well, so that the vectors are not only orthogonal, but they're unit vectors. So then the result is the same thing as what we had before. S is going to be equal to Q, and the lambda matrix is going to be 11, 0, 0, 1, and then Q transpose. Right, and so just for completeness sake, let me write this whole thing out. The S is going to be, I have a 1, 3, and a negative 3, 1, and then I have a 1 over square root of 10, right? And then my lambda is going to be 11, 0, 0, 1. Those are my eigenvalues. And then the transpose here. So this is going to be a 1, 3, and a negative 3, 1. And then I have a 1 over square root of 10. Looks like that. I can combine, of course, the 1 over square root of 10s, and this whole thing would just be 1/10, and then rewrite these matrices. So, and if you want to verify that this is correct, you can multiply all of this out, and when you do all this multiplication, we will end up with our symmetric matrix. So just another example to give you a demonstration of how this works. Okay, thanks.